somewhere in the constellation of Centaurus. 145 million light-years from where you're sitting right now, there is a hole in the universe. Not a hole in space, exactly. A hole in the normal rules of physics. A place where matter doesn't just fall. It is devoured, compressed, and erased from the observable universe, one atom at a time, forever. It has a mass more than 300 million times that of our sun. If you could somehow stand at a safe distance and watch it work, you would see something almost impossible to put into words. A whirlpool of white-hot gas, spinning so fast it glows, spiraling down into a darkness that swallows even light itself. This is a supermassive black hole, and for over half a century, it has been quietly humiliating astronomers. Not because we couldn't find them, we found thousands. Not because we couldn't weigh them, or map them, or watch them erupt in jets of energy that stretch for hundreds of thousands of light years. We've done all of that. The problem was simpler and far more embarrassing. We didn't know how they eat. Every large galaxy in the universe, including our own Milky Way, has one of these monsters sitting at its center. And somehow, over billions of years, those monsters grew from modest seeds into objects millions of billions of times heavier than our sun. To do that, they needed fuel. A steady, reliable, uninterrupted diet of gas, falling inward, generation after generation. But there was a catch. A black hole that's actively feeding doesn't do so quietly. It switches on like a furnace. It blasts out jets of energy, so powerful they can blow gas out of an entire galaxy. And that should be a problem, because that same gas is exactly what the black hole needs to keep eating. It's a little like a fire that burns so hot, should incinerate its own firewood before it can be used. So here was the puzzle. If black holes heat and expel the very fuel they depend on, how do they keep growing for billions of years without starving? How does the fire keep burning? For decades, this question sat unanswered. A gap in one of the most important processes in the universe, the process that connects the smallest scales of physics to the largest structures in the cosmos. And then, in the summer of 2026, the James Webb Space Telescope pointed its most sensitive instrument at a galaxy called NGC 4696 and stared. For nearly 8 hours, without blinking, it watched the black hole at that galaxy's center. And what it saw was the missing piece. A river of gas, cooling out of the galaxy's superheated atmosphere, collapsing into thin glowing filaments, and pouring, like water down a drain, directly into a spinning disk of material just 800 light-years across, feeding the black hole in real time. For the first time in the history of astronomy, we were not looking at a black hole's meal after the fact. We were watching the meal being served. This is the story of that discovery. It's a story about galaxies and gravity, about jets of plasma and rivers of gas, too faint for any telescope before Webb to resolve. It's a story about a 100-year-old mystery, a battle-scarred cluster of galaxies, and a spacecraft parked 1 million miles from Earth that just handed us the clearest answer yet to one of the biggest open questions in astrophysics. How does a black hole keep feeding itself? Stick with me for the next hour and a half, because to really understand what Webb found, we need to start from the very beginning. We need to understand what a supermassive black hole actually is, why they're so hard to feed, why astronomers have been chasing this mystery since the 1970s, and why one particular galaxy, sitting quietly in a galaxy cluster you've probably never heard of, turned out to be the perfect place to finally catch a black hole in the act. Let's begin. Let's start with the basics, because even the word black hole tends to conjure the wrong picture in most people's minds. It's not a cosmic vacuum cleaner. It's not going to wander through the galaxy sucking up planets. A black hole is, at its core, shockingly simple. It's what's left when an enormous amount of mass gets crushed into an impossibly small space. Gravity is a warping of space and time caused by mass. The more mass you pack into a given volume, the more extreme that warping becomes. Squeeze enough matter into a small enough region, and eventually you reach a point where the warping becomes so severe that not even light, the fastest thing in the universe, has enough speed to escape. That boundary is called the event horizon. Cross it, and there is no coming back. Not because of some invisible law, but because every possible path through space and time on the far side of that boundary leads only inward. Stellar mass black holes are the ones astronomers understand best. They form when a massive star, many times heavier than our Sun, runs out of nuclear fuel and collapses under its own gravity. These black holes typically weigh somewhere between 5 and a few dozen times the mass of the Sun. We've detected them directly now, thanks to gravitational wave observatories like LIGO and Virgo, which pick up the ripples in space-time produced when two of these objects spiral into each other and merge. But there is another class of black hole entirely, and it operates on a completely different scale. Supermassive black holes don't weigh a few dozen solar masses. They weigh millions, sometimes billions of solar masses. The one at the center of our own Milky Way, called Sagittarius A star, weighs in at about 4 million times the mass of the Sun, and we now have direct images of it, captured by the Event Horizon Telescope. The black hole at the center of the galaxy M87 is even larger, about 6.5 billion solar masses, so big that its shadow was the first black hole image ever captured back in 2019. Here's the thing that should stop you in your tracks. Almost every large galaxy in the observable universe has one of these supermassive giants sitting at its center. Not most, not many, nearly all of them. It appears to be a fundamental feature of how galaxies are built, as if you cannot construct a galaxy the size of the Milky Way or larger without also constructing somewhere in its heart an object with the gravitational authority of millions of suns compressed into a region smaller than our solar system. That fact alone raises an enormous question. Where did these things come from? And more specifically for our story today, how did they get so big? A black hole doesn't grow by magic. It grows the same way anything grows, by adding mass. In this case, that means gas, dust, and occasionally entire stars falling into it over time. Astronomers call this process accretion, and the swirling disk of infalling material that forms around a feeding black hole is called an accretion disk. Now, you might imagine that gas just falls straight in, like a rock dropped down a well. But that's not how it works, because almost nothing in space falls in a perfectly straight line. Gas orbiting a black hole retains some angular momentum, some sideways motion, left over from whatever set it moving in the first place. Because of that leftover spin, instead of plunging directly in, the gas settles into a flattened, rotating disk, similar to how water spirals around a drain instead of falling straight down. Within that disk, friction and turbulence and magnetic fields slowly drain away the gas's angular momentum, allowing it to spiral inward bit by bit, getting hotter and hotter as it approaches the black hole. By the time gas reaches the inner edge of the disk, just before it crosses the event horizon, it has often been heated to millions of degrees, hot enough to glow brilliantly across the electromagnetic spectrum, from radio waves all the way up to X-rays. This is why actively feeding supermassive black holes are some of the brightest, most energetic objects in the entire universe. They're called active galactic nuclei, or AGN for short, and when the feeding is especially intense, the object is sometimes called a quasar, a term that in the 1960s literally meant quasi-stellar radio source, because early radio astronomers had no idea what these impossibly bright, impossibly distant points of light actually were. It would take years to realize that quasars were not strange stars in our own galaxy, but the blazing cores of galaxies, billions of light years away, powered by black holes actively devouring matter at incredible rates. So that's the basic picture. Supermassive black holes sit at the centers of galaxies. When they feed, the infalling gas forms a hot, glowing accretion disk. And over cosmic time, through repeated episodes of feeding, these black holes grow from relatively modest beginnings into the millions or billions of solar mass giants we observe today. Simple enough, right? Except it isn't, because the moment a black hole starts feeding in earnest, it does something that seems, on the face of it, completely self-defeating. When a supermassive black hole feeds, it doesn't just quietly absorb material. It throws a tantrum. As gas spirals through the accretion disk, powerful magnetic fields get twisted and wound up by the disk's rotation, and some of that energy gets channeled into narrow, focused beams of particles that shoot outward from the black hole's poles at speeds approaching the speed of light. These are called relativistic jets, and they are, without exaggeration, some of the most extreme phenomena in nature. Some of these jets extend for hundreds of thousands, even millions of light years, vastly larger than the galaxy that produced them. They plow through the surrounding gas like a fire hose blasting through fog, carving out bubbles and cavities, heating everything they touch to tens of millions of degrees. Now think about what that means for the black hole's food supply. Surrounding every large galaxy, especially the giant elliptical galaxies found at the centers of galaxy clusters, is a vast reservoir of hot gas, sometimes called the intracluster medium, or the galaxy's hot atmosphere. This gas is the raw material that could, in principle, cool down, fall inward, and feed the central black hole. It's the pantry. But when the black hole fires up its jets, it dumps enormous amounts of energy directly into that pantry. The jets inflate huge bubbles of hot plasma. They send shock waves rippling outward. They can heat gas that was on the verge of cooling and falling inward, and instead puff it back up, keeping it hot, diffuse, and stubbornly resistant to collapse. This is what astronomers call a GN feedback, and it creates what looks, at first glance, like a genuine paradox. The black hole needs cool, dense gas to fall inward and feed it. But the very act of feeding produces jets that heat the surrounding gas and prevent it from cooling and falling inward. It's a bit like a campfire that, every time it burns a log, blasts out a wave of heat so intense it dries out and scatters all the nearby firewood, making it harder to burn the next log. If this feedback were simply a one-way street, heating gas and pushing it away forever, you'd expect black hole growth to be a self-limiting, short-lived affair. The black hole switches on, blasts away its fuel supply, and then sits there starving, unable to grow further, for the rest of cosmic history. But that's not what we see. We see black holes that have clearly grown to enormous sizes over billions of years. Some of them still actively feeding today, still launching jets, still glowing as active galactic nuclei billions of years after they first switched on. Something must be resupplying them. Something must be closing the loop, taking gas that was heated and expelled, and eventually returning it, cooled and condensed, back to the black hole's doorstep. This is sometimes described by astronomers using an analogy to biology, a self-regulating feedback loop, not unlike a thermostat. The black hole feeds, heats the surrounding gas, and effectively turns down its own furnace. The gas then gradually cools over time. As it cools, it becomes denser, clumpier, more prone to collapsing under gravity. Eventually, cooled gas rains back down toward the center, restarting the feeding process, restarting the jets, and the whole cycle begins again. Astronomers have had strong theoretical reasons to believe something like this must be happening for decades. Computer simulations of galaxy formation that don't include this kind of feedback loop produce galaxies that are wildly, catastrophically wrong compared to what we actually observe. Galaxies that are far too massive, with far too many stars, because without a black hole's heating and cooling cycle to regulate things, gas just keeps cooling and forming stars without limit. so theorists were confident the cycle existed. What they lacked, for the better part of half a century, was direct observational proof. Nobody had actually watched cooled gas condense out of a hot atmosphere, form into coherent structures, and flow all the way down into the feeding zone of a black hole. We had pieces of the puzzle: hot gas here, jets there, occasional filaments of cooler gas glimpsed in older images. But we had never traced the entire pathway, from a galaxy's hot atmosphere, down through condensing filaments, into the spinning disk that directly feeds the black hole. That is precisely the gap that the new James Webb observations of NGC 4696 were designed to fill. And to understand why this particular galaxy was chosen, and why it took a telescope as powerful as Webb to finally see the answer, we need to talk about where NGC 4696 sits in the universe, and what earlier telescopes had already managed to find there. To find a black hole caught in the act of feeding, you need the right kind of neighborhood. And it turns out that some of the best places in the universe to study this process are found not in isolated galaxies floating alone in space, but at the crowded centers of massive galaxy clusters. A galaxy cluster is exactly what it sounds like: a gravitationally bound collection of hundreds, sometimes thousands of galaxies, all orbiting a common center of mass. Clusters are the largest gravitationally bound structures in the universe, and they're embedded in enormous clouds of superheated gas so hot, tens of millions of degrees, that it glows brightly in X-rays. This is the intracluster medium we mentioned earlier, and at the center of many clusters, sitting at the very bottom of the cluster's gravitational well, you'll typically find one enormous elliptical galaxy, often called the brightest cluster galaxy, or BCG. These central galaxies are cosmic giants in their own right, built up over billions of years by swallowing smaller galaxies and channeling inflowing gas from the surrounding cluster medium. And because they sit at the bottom of such a deep gravitational well, with such a vast reservoir of hot gas surrounding them, they are exactly the kind of environment where you'd expect a GN feedback and gas cooling to be locked in a constant, dramatic tug of war. The Centaurus Cluster is one of these systems. It's located, as the name suggests, in the constellation Centaurus, roughly 145 million light-years from Earth, which, on cosmic scales, is practically next door. That's close enough that astronomers can resolve fine details within the cluster that would be hopelessly blurred together in a more distant system. At the heart of the Centaurus Cluster sits NGC 4696, the cluster's brightest and most massive galaxy. Long before Webb ever turned its instruments toward it, NGC 4696 had already earned a reputation among astronomers as one of the most interesting objects of its kind. X-ray observatories like Chandra had revealed intricate structures in the hot gas surrounding the galaxy, spiral-shaped ripples and folds, evidence of past interactions between the black hole's jets and the surrounding atmosphere, like fossilized footprints of feeding episodes stretching back millions of years. And then there was Hubble. Long before Webb existed, the Hubble Space Telescope had already pointed its cameras at the center of NGC 4696 and captured something strange: a network of dusty, filamentary structures threading through the galaxy's core, including a peculiar hook-shaped or S-shaped swirl of material curling around the presumed location of the central black hole. Hubble's images were beautiful, and they were tantalizing. They showed, unmistakably, that there was structure here, some kind of organized flow of material near the black hole, rather than a smooth, featureless blob of gas. But Hubble's instruments, powerful as they were, could only show researchers the shape of these filaments. They couldn't tell astronomers how the gas within those filaments was actually moving. Was it falling inward toward the black hole? Was it being blown outward by the jets? Was it just sitting there, suspended, going nowhere? That distinction matters enormously. A filament that looks, in a still image, exactly like an inflow could in reality be gas caught in an outflow or gas orbiting in some unrelated pattern entirely. A snapshot can show you shape. It cannot, by itself, show you motion. And motion, specifically, the question of whether gas was flowing inward to feed the black hole, was the entire point. To measure motion, astronomers need something more than a pretty picture. They need spectroscopy, the ability to split incoming light into its component wavelengths and measure incredibly subtle shifts in that light caused by the Doppler effect, the same phenomenon that changes the pitch of an ambulance siren as it drives toward you and then away. Light from gas moving toward us gets shifted slightly toward the blue end of the spectrum. Light from gas moving away gets shifted slightly toward the red. By measuring these tiny shifts across every part of an object, astronomers can build up a complete map, not just of what something looks like, but of how every part of it is moving. Hubble had given the world a striking photograph of NGC 4696's central swirl. What the field needed next was a spectrograph sensitive enough and a telescope large enough to trace the actual motion of gas within that swirl and to follow that motion outward along the filaments all the way back to wherever the gas was originally coming from. That instrument, it turned out, already existed. It had launched on Christmas Day, 2021, and it was still, in the summer of 2026, delivering some of the most important discoveries in the history of astrophysics. Its name is the James Webb Space Telescope, and one of its 4 science instruments, a device called NIRSpec, was about to become the key that finally unlocked NGC 4696's secret. Let's talk for a moment about why the James Webb Space Telescope was uniquely suited to crack this particular mystery, because understanding the tool tells you a lot about why the discovery took as long as it did. Webb is, first and foremost, an infrared telescope. Unlike Hubble, which primarily observes visible and ultraviolet light, Webb is optimized to detect infrared radiation, wavelengths of light longer than what the human eye can see. This isn't a minor technical detail. It's central to almost everything Webb has been able to accomplish. Infrared light has a special property. It can pass through clouds of dust and gas that would completely block visible light. Think about how a thick fog can hide a mountain from your eyes, but a thermal camera can still detect the heat radiating through that fog. Infrared observations let astronomers peer through exactly the kind of dusty, gas-filled environments found at the cores of galaxies, the very regions where black holes live and feed. Webb's primary mirror, 6.5 meters across and built from 18 hexagonal gold-coated segments, is the largest mirror ever launched into space, giving it far greater light-gathering power and sharper resolution than Hubble, particularly at these longer infrared wavelengths. And crucially, Webb doesn't just take pictures. It carries an instrument specifically built to dissect light and extract motion, chemistry, and physical conditions from it. That instrument is called NIRSpec, the Near-Infrared Spectrograph. Here's what makes NIRSpec special. A camera captures an image, light intensity across a 2-dimensional field. A spectrograph does something more sophisticated. It takes incoming light and spreads it out into its full rainbow of component wavelengths, the same way a prism splits white sunlight into a rainbow. But NIRSpec doesn't just do this for a single point of light. It's an integral field spectrograph, which means it can simultaneously capture a complete spectrum for every single pixel across a 2-dimensional field of view. Think about what that means in practice. Instead of getting one photograph and one spectrum, astronomers using NIRSpec effectively get a 3-dimensional data cube, 2 spatial dimensions, showing where on the sky the light is coming from, and a 3rd dimension of wavelength, showing the full spectral fingerprint of the gas at every single point in that image. From that data cube, researchers can reconstruct, essentially pixel by pixel, how fast gas is moving, whether it's moving toward us or away from us, what temperature it is, and what it's made of. This capability turned out to be exactly what was needed to finally settle the question that Hubble's images had raised, but couldn't answer. Where Hubble showed shape, an NIRSpec could reveal motion in exquisite detail across the entire swirling structure at the heart of NGC 4696. The team behind this observation, an international collaboration led by researchers at the Université de Montréal, with significant contributions from Michigan State University and the University of Nottingham, among other institutions, dedicated an extraordinary amount of Webb's precious observing time to this single target. Telescope time on Webb is one of the most competitive and valuable resources in modern science. Every hour is requested by dozens of competing research teams, and only a small fraction of proposals are ever approved. For this project, the team was granted close to 8 hours of continuous observation with NIRSpec, pointed squarely at the heart of NGC 4696. 8 hours might not sound like a long time by everyday standards, but in the world of space-based spectroscopy, it's a substantial investment, long enough to gather incredibly faint signals from gas that, despite glowing in infrared light, is still spread thin across hundreds of light years, making it a genuinely challenging target, even for an instrument as sensitive as an NIRSpec. The payoff for that investment was extraordinary. NIRSpec was able to resolve structures in the gas around NGC 4696's black hole down to a scale of roughly 30 light years, an almost unbelievable level of precision for an object 145 million light years away. To put that in perspective, 30 light years is roughly the distance from our Sun to a handful of the nearest stars in our own galactic neighborhood. Webb was resolving structures on that scale, in a galaxy so distant that its light left before humans had learned to smelt bronze many times over, light that had been traveling toward Earth for 145 million years. Since long before there were dinosaurs walking on this planet, arriving now, finally, to be captured by a golden mirror parked 1 million miles from Earth. With that level of detail, and with the ability to measure the velocity of gas at every single point in the field, the research team was finally in a position to answer the question Hubble's images had left open. Was the swirling, hook-shaped structure at the center of NGC 4696 actually connected to a larger inflow of gas? And if so, was that gas really falling inward, feeding the black hole, exactly as decades of theory had predicted? The answer, when it came, was about to rewrite the textbook. Let's walk through the actual observations, step by step, because this is the heart of the story. When the research team processed the NIRSpec data, they were looking specifically for the emission signatures of warm, ionized gas that has been energized enough that its atoms have lost electrons, causing it to glow at very specific well-known wavelengths of infrared light. By measuring the precise wavelength of this glowing gas at every point across the field of view, and comparing it to the wavelength that same gas would emit if it were standing perfectly still, the team could calculate a velocity map, a picture not of where the gas is, but of how fast it's moving and in which direction across the entire structure. The results confirmed something dramatic. That hook-shaped, C-shaped swirl that Hubble had photographed years earlier wasn't just a static, decorative structure. It was, in fact, a rotating disk of gas, a genuine circumnuclear disk, spinning around the supermassive black hole at truly staggering speeds. The data showed gas within this disk moving at velocities up to roughly 600 kilometers per second. To put that in perspective, that's over 2 million kilometers per hour, more than 1,300,000 miles per hour. At that speed, you could cross the entire continental United States in about 8 seconds. This spinning disk measures roughly 800 light years across. That's an almost incomprehensible structure when you actually sit with the number. A disk of glowing, whirling gas 800 light-years in diameter, tightly wound around a black hole, delivering material to it in a slow, disciplined spiral. The same basic physical process that governs water circling a drain, just scaled up to a size that would engulf hundreds of star systems. But the disk itself, dramatic as it is, wasn't actually the biggest surprise. Astronomers had long suspected that black holes at the centers of galaxies like this one were surrounded by some kind of rotating disk of material. What they had never directly confirmed was where that disk's fuel was actually coming from, moment to moment in real time. And this is where the NIRSpec data delivered its key result. Tracing the velocity map outward from the spinning disk, the team found a large-scale filament of gas, a long, coherent stream extending well beyond the disk itself, out into the surrounding galaxy. And crucially, the gas within that filament was moving in exactly the direction you'd expect if it were falling inward, feeding directly into the spinning disk. In other words, Webb didn't just find a disk. It found the disk connected, physically and dynamically, to an inflowing stream of gas, a filament actively delivering fresh material from the galaxy's wider surroundings down into the black hole's immediate feeding zone. The filament and the disk were not two separate, unrelated features sitting near each other by coincidence. They were one continuous flow, gas falling inward along the filament, funneling smoothly into the rotating disk, and from there, presumably, continuing its slow inward spiral toward the black hole itself. This is the observation that researchers had been chasing for decades, not indirect evidence, not a plausible-looking shape in a still photograph. An actual measured, moving river of gas, caught mid-flow, tracked all the way from the outer filament into the black hole's feeding disk. Helen Russell, an astrophysicist at the University of Nottingham and a member of the research team, described the significance of this result in terms that are worth repeating carefully. According to Russell, Webb was finally showing researchers the final link in a closed loop. A loop where a vast filamentary network of gas ultimately funnels material down into a disk that, in turn, fuels the black hole. That phrase, the final link in a closed loop, is really the crux of the entire story, and it's worth pausing to unpack exactly what it means. For years, astronomers had pieces of this loop. They could observe jets erupting from active black holes, heating the surrounding gas. They could observe, through X-ray telescopes like Chandra, that gas in galaxy clusters does gradually cool over time, forming denser, cooler pockets within the otherwise blazing hot cluster atmosphere. And they had glimpsed, in earlier Hubble images, filaments of cooler gas and dust threading through these environments, looking for all the world like they might be falling inward. What nobody had managed to do before was connect every one of those pieces into a single, continuous, physically verified pathway: heating, cooling, filament formation, inward flow, and delivery into the feeding disk, all traced within one system, using actual velocity measurements rather than inference from still images. NGC 4696 gave the team that complete picture. And to understand exactly why this particular pattern of gas motion was so convincing, and not just a coincidental alignment, the team didn't stop with the observations alone. They went a step further and built a computer simulation of the entire system to test whether this exact configuration of infalling filament and spinning disk was actually physically plausible. Observations alone, no matter how detailed, can only tell you what a system looks like and how it's moving at the single moment you happen to observe it. They can't, by themselves, tell you why the gas is arranged the way it is, or whether the pattern you're seeing is a stable, ongoing process, or some kind of fleeting, one-off coincidence. To bridge that gap, the research team turned to three-dimensional magnetohydrodynamic simulations, a term that sounds intimidating, but really just means computer models that simultaneously track how gas moves, or hydrodynamics, and how magnetic fields influence and are influenced by that moving gas, or magneto. These simulations are built from the fundamental laws of physics, gravity, fluid dynamics, thermodynamics, and electromagnetism, and then run forward in time on powerful supercomputers, allowing researchers to essentially create a virtual version of NGC 4696's environment and watch what happens. The team tailored their simulation specifically to match the conditions believed to exist around NGC 4696's black hole, a hot, diffuse atmosphere of gas surrounding the galaxy's core, a supermassive black hole with jets capable of heating that surrounding gas, and the physical processes that allow portions of that gas to cool, condense, and collapse under gravity. When they ran the simulation, something remarkable happened. The model, built independently from first principles of physics, rather than tuned to match the observations, produced exactly the kind of structure Webb had actually observed. Gas cooling out of the hot atmosphere, collapsing into thin, elongated filaments, and those filaments feeding into a rotating disk around the central black hole. The simulated filament and disk system closely resembled the real one captured by NIRSpec, both in overall shape and in the general pattern of gas motion. This kind of agreement between an independent theoretical model and a hard observational result is enormously significant in science. It's the difference between saying, "Here's an interesting pattern we noticed," and saying, "Here's a pattern we noticed," and it's also exactly what the underlying physics predicts should happen. When a simulation built from fundamental physical laws reproduces a specific, previously unconfirmed structure, and then that exact structure shows up in real observational data, it gives researchers much stronger confidence that they're not looking at a coincidence or a misinterpretation of noisy data, but a real physical process playing out as expected. The simulations also revealed something else that turned out to be crucial: the role of magnetic fields in guiding this whole process. It's easy to think of gas falling toward a black hole as a purely gravitational affair. Mass attracts mass, gas falls inward, end of story. But real astrophysical gas isn't a simple neutral fluid. Much of it is ionized, meaning it carries an electric charge, and charged, moving gas interacts strongly with magnetic fields. According to the simulations, magnetic fields threading through the galaxy's hot atmosphere play an active role in shaping how cooling gas condenses and funnels inward. Rather than falling in a smooth, symmetric, spherical rain toward the black hole from every direction at once, magnetically influenced gas tends to be channeled and guided along specific pathways, forming the kind of narrow, elongated filaments actually observed by Webb, rather than a diffuse, unstructured cloud. The magnetic fields essentially act like plumbing, directing the flow of cooling gas along preferred channels, concentrating it into coherent streams rather than letting it spread out and disperse. This detail matters because it helps explain one of the long-standing puzzles about how black hole feeding actually works at a physical level. Simple models of gas accretion, sometimes called Bondi accretion, named after the astrophysicist Hermann Bondi, who worked out the mathematics of spherically symmetric gas infall back in the 1950s, assume that hot gas falls smoothly and directly inward toward a central mass in a roughly spherical pattern. But the structures Webb observed around NGC 4696 don't look anything like a smooth spherical inflow. They look like discrete, organized filaments feeding into an organized, rotating disk. This suggests that in systems like NGC 4696, simple Bondi-style accretion may not be the dominant process governing how the black hole gets fed. Instead, the fueling process appears to be substantially more structured, shaped by the complex interplay of cooling instabilities, gravity, and magnetic fields, producing exactly the kind of clumpy, filamentary, disk-feeding pattern that Webb managed to directly observe and measure for essentially the first time. Taken together, the direct velocity measurements from NIRSpec, and the independent confirmation from magnetohydrodynamic simulations, the research team had assembled about as complete a picture as modern astrophysics could hope to produce of a single feeding episode around a supermassive black hole. Hot gas, heated by past jet activity, cooling gradually within the galaxy's atmosphere. That cooling gas condensing into magnetically guided filaments. Those filaments flowing inward and merging into a spinning, 800 light-year wide disk. And that disk, presumably, continuing to funnel material the rest of the way down toward the black hole's event horizon, restarting the cycle of feeding, jet activity, heating, and eventual recooling all over again. It's worth sitting with the elegance of that picture for a moment, because it resolves what had looked for decades like a genuine contradiction. The black hole's own feeding process seems, at first glance, self-destructive. It heats and disperses the very gas it needs. But what NGC 4696 reveals is that this isn't destruction at all. It's recycling. The energy the black hole releases doesn't destroy its fuel supply. It merely delays the fuel's return, sending it out to cool, condense, and eventually flow back home. Let's put the whole cycle together now, from start to finish, because once you see it as a complete loop, the elegance of it becomes almost impossible to miss. Step 1. The black hole feeds. Material from its accretion disk spirals inward and crosses the event horizon, releasing enormous amounts of energy in the process, some of which gets channeled into powerful jets, blasting outward from the black hole's poles. Step 2. Those jets slam into the surrounding hot atmosphere of gas that envelops the galaxy, depositing enormous amounts of energy and heating that gas even further, inflating bubbles and cavities, and effectively cutting off, at least temporarily, any easy pathway for that gas to cool and fall back inward. Step 3. Over time, and we're talking about timescales of millions of years here, not days or centuries, the jet activity subsides, or at least becomes less intense in a given region, and portions of that superheated gas slowly begin to radiate away their energy and cool. As gas cools, it becomes denser, and denser gas is more susceptible to a runaway process called thermal instability, where slightly cooler, slightly denser pockets of gas cool even faster than their surroundings, in a kind of runaway feedback loop that causes them to condense out of the hot atmosphere entirely, forming isolated clumps and filaments of much cooler, denser material embedded within the still hot surrounding gas. Step 4. Guided by gravity and channeled by magnetic fields, these condensing filaments of cooler gas begin to fall inward, toward the deepest point of the galaxy's gravitational well, toward the black hole. As they fall, they stretch out into the kind of long, thin, coherent streams that Webb directly observed and measured. Step 5. As these infalling filaments approach the black hole, they merge into a rotating disk, the circumnuclear disk, spinning at hundreds of kilometers per second, exactly as observed in NGC 4696. This disk acts as a kind of staging area, a final holding pattern where infalling gas accumulates and gradually spirals the rest of the way inward. Step 6. Material from that disk eventually reaches the black hole itself, restarting active feeding, restarting the jets, and the entire cycle begins again. Heat, cool, condense, fall, feed, heat, over and over, potentially for billions of years. This is why, in coverage of this discovery, several astronomers use the phrase cosmic recycler to describe what black holes like the one in NGC 4696 appear to be doing. It's a genuinely apt description. Rather than a black hole simply burning through a finite fuel supply and eventually running dry, the way you might picture a car running out of gas, these systems appear to be running on a renewable cycle, where the black hole's own waste heat drives the process that eventually resupplies it. There's something almost thermostatic, about the whole arrangement. And in fact, that's exactly the analogy many researchers reach for. A home thermostat doesn't just blast heat forever, and it doesn't just switch off forever either. It monitors the temperature, switches the furnace on when things get too cold, switches it off when things get too warm, and settles into a rough equilibrium over time. Black holes and their surrounding gas atmospheres appear to behave in a strikingly similar way. Too much cooling, and gas piles up, falls inward, and triggers a burst of feeding and jet activity. Too much jet activity, and the surrounding gas gets overheated and puffed up, temporarily shutting off the supply until it cools again. This self-regulating loop is not just an interesting curiosity about one particular galaxy. It appears to be one of the fundamental mechanisms by which supermassive black holes have managed to grow to enormous sizes over cosmic history, all while avoiding two very different failure modes that theorists have long worried about. The first failure mode is what we might call runaway starvation, a black hole that heats and permanently expels its fuel supply, with no mechanism for that gas to ever return, leaving the black hole stuck at whatever mass it had already reached, unable to grow further. If this were the typical outcome, we would expect most supermassive black holes to be relatively small and to have stopped growing relatively early in cosmic history. The second failure mode is the opposite, runaway growth, where gas cools and falls inward without any check or balance, fueling an ever more massive black hole that keeps consuming everything nearby without limit, producing galaxies with black holes and stellar populations far more massive than anything we actually observe in the real universe. Simulations of galaxy formation that omit AGN feedback altogether reliably produce galaxies like this, overgrown, unrealistic, and clearly at odds with real observational data. The self-regulating cycle observed in NGC 4696 threads the needle between these two extremes. It provides just enough feedback to prevent runaway, unchecked growth, while still allowing gas to periodically cool and resupply the black hole, enabling continued growth over enormously long timescales, stretched out across billions of years in fits and starts, rather than either a single unstoppable binge or a permanent terminal famine. This is, in a very real sense, how the universe keeps its books balanced. It's a mechanism that helps explain not just how individual black holes grow, but why galaxies across the universe tend to settle into remarkably consistent relationships between the mass of their central black hole and the properties of the galaxy surrounding it. A set of correlations astronomers have observed for decades, without ever having direct evidence, until now, the physical process actually enforcing that balance in real time. Now, here's where this discovery connects to one of the most puzzling frontiers in all of modern astrophysics, a puzzle that Webb itself has actually made worse, in a sense, even as it's been busy solving other mysteries. Standard models of black hole growth generally assume a fairly patient, gradual process. Even under favorable, unimpeded conditions, most theoretical models suggest it should take on the order of 1 billion years or more for a black hole to grow, from a modest seed into something in the range of 1 billion solar masses, simply because there are physical limits on how fast gas can be funneled into a black hole without the radiation pressure from all that infalling, glowing material actually pushing additional gas away, a natural speed limit sometimes called the Eddington limit. And yet, since it began science operations in 2022, Webb has repeatedly found something that shouldn't, by that standard timeline, be possible. It has detected supermassive black holes that appear to have already grown to enormous masses, hundreds of millions, even billions of times the mass of the Sun, at a point in cosmic history when the universe itself was less than 1 billion years old. Some of the most extreme examples appear to have assembled that much mass within just a few 100 million years of the Big Bang. This is a serious problem for standard accretion theory. If black holes can only grow so fast, limited by the physics of radiation pressure and gas supply, then finding fully formed billion solar mass giants when the universe was still in its infancy suggests that either our black hole seeds started out far larger than we assumed, or that black holes are somehow capable of growing dramatically faster than standard theory predicts, or some combination of both. A black hole that can reliably and repeatedly resupply itself, drawing cooled gas back in almost as fast as it heats and disperses it, is a black hole that spends less of its existence sitting idle, starved of fuel, waiting for conditions to improve. Instead of long stretches of dormancy between feeding episodes, a black hole operating an efficient recycling loop like the one observed in NGC 4696 could, in principle, sustain nearly continuous growth, punctuated by only brief pauses, rather than the long famines that simpler models often assume. It's important to be careful here and honest about the limits of what this particular discovery does and does not tell us. NGC 4696 is a relatively nearby galaxy, observed as it exists in the present-day local universe, roughly 145 million years in our past, which sounds like a long time, but is a tiny sliver compared to the roughly 13.8 billion years since the Big Bang. This observation does not, by itself, prove that early universe black holes, forming and growing within the first billion years of cosmic history, were relying on exactly this same mechanism. The conditions in the early universe, denser gas, different chemical compositions, more frequent galaxy mergers, were in many ways quite different from the relatively settled, mature environment of a present-day galaxy cluster like Centaurus. But what this discovery does provide is something arguably just as valuable: a real, physically verified example of how a self-regulating feeding cycle can actually work in practice, rather than just in theoretical models. It gives astronomers a concrete, observationally grounded template, an actual working example, with actual measured velocities and actual confirmed filament-to-disk connections that can now be used to refine and test the computer simulations astronomers rely on to model black hole growth throughout cosmic history, including in the early universe. If similar filament-fed disks turn out to be common in other galaxies, including more distant ones observed as they appeared earlier in cosmic history, it would lend significant support to the idea that efficient, self-sustaining gas recycling has been a persistent feature of black hole growth since very early times, potentially helping to explain, at least in part, how some black holes managed to grow so audaciously fast, so early, in a universe that was still very young. This is really the broader significance of what might otherwise look like a fairly specialized, technical result about the gas dynamics in one particular galaxy. It's a piece of a much larger puzzle, one that stretches from the local universe, right here in our cosmic backyard, all the way back to the first billion years after the Big Bang, and the still unresolved question of how the universe's earliest monster black holes managed to grow up so fast. Every great discovery in astronomy is, in the end, the product of a lot of very specific, very human work: proposal writing, telescope scheduling, months of careful data reduction, endless cross-checking against simulations, and a great deal of patient argument among collaborators about what the data actually shows. It's worth taking a moment to talk about the team behind this result. The research was led by an international collaboration headquartered at the Université de Montréal, with substantial contributions from Michigan State University and the University of Nottingham in the United Kingdom, along with researchers from a number of other institutions. This is fairly typical of how modern observational astrophysics works. Projects like this one require an enormous range of specialized expertise. People who understand the technical operation of NIRSpec and how to properly calibrate and reduce its data. People who specialize in the physics of hot cluster gas and AGN feedback. People skilled in building and running magnetohydrodynamic simulations. and people with deep experience in the specific history and prior observations of the Centaurus Cluster and NGC 4696 itself. No single researcher, however brilliant, could realistically bring all of that expertise to bear alone. Megan Donahue, a university distinguished professor of physics and astronomy at Michigan State, offered a comment about the sheer scale of information Webb has been generating that's worth repeating, because it captures something true about the current moment in astronomy generally, not just this one result. She noted that Webb's observations are delivering thousands of new facts and measurements, and that keeping up with it all, processing everything the telescope is capable of revealing, is genuinely a lot to absorb. That's not a complaint. It's closer to a description of what a golden age of discovery actually feels like from the inside. Webb has been in operation for a relatively short time, several years now, and in that time, it has repeatedly delivered results that either overturn or dramatically refine long-standing assumptions across nearly every area of astrophysics it touches, from the atmospheres of exoplanets to the earliest galaxies in the universe, to, as we've spent the last hour discussing, the detailed physics of how supermassive black holes are fed. Helen Russell's framing of the result, describing Webb as finally revealing the final link in a closed loop, reflects years of prior work by many researchers, herself included, studying AGN feedback in galaxy clusters using X-ray telescopes like Chandra and XM-Mu, radio telescopes tracing the extent of black hole jets, and earlier infrared and optical observations from telescopes like Hubble. The NGC 4696 result didn't emerge from nowhere. It's the culmination of a research program that's been building piece by piece for the better part of 2 decades, with each new telescope and each new observation adding another fragment to a puzzle that Webb was finally powerful enough to complete. The results were published in the Astrophysical Journal Letters, one of the leading peer-reviewed journals in the field, meaning the work was independently scrutinized by other expert astronomers. Before publication, a process designed to catch errors, challenge weak arguments, and ensure that claims presented as significant discoveries can actually withstand rigorous, informed criticism. That process matters. It's part of why a result like this one carries real scientific weight, rather than being just an interesting but unverified claim. NGC 4696 isn't the only galaxy cluster where astronomers have caught glimpses of black hole feedback in action, and it's worth briefly touring some of the other landmark observations in this field, because they help show just how much of a leap forward this particular result represents. Perhaps the most famous example of a GN feedback in a galaxy cluster comes from the Perseus cluster, roughly 240 million light-years away. Chandra X-ray observatory images of Perseus revealed enormous cavities, or bubbles, carved into the hot cluster gas by the central black hole's jets, some of these cavities large enough to swallow entire galaxies. Even more remarkably, astronomers detected sound waves rippling outward through the cluster's hot gas, generated by the repeated eruptions from the central black hole at a pitch far too low for any human ear to ever hear, roughly 57 octaves below middle C, translated in a famous sonification into an audible tone that briefly became something of an internet sensation. Perseus gave astronomers dramatic, unmistakable evidence that black hole jets really do dump enormous amounts of energy into their surrounding environment, heating and reshaping the hot gas on scales of tens of thousands of light-years. Then there's M87, home to the black hole made famous by the Event Horizon Telescope's historic 2019 image, the first direct image of a black hole's shadow ever captured. M87 also hosts one of the most striking, well-studied relativistic jets in the sky, a brilliant blue streak of plasma extending thousands of light-years from the galaxy's core, visible even in relatively modest telescopes. M87 has taught astronomers an enormous amount about the structure and physics of black hole jets themselves, how they're launched, how they're collimated into such narrow, coherent beams, and how they interact with their surrounding environment. What these earlier landmark observations, Perseus and M87 among them, provided was strong evidence for one half of the feeding cycle, the outward heating half. Jets erupting, energy being dumped into surrounding gas, cavities being carved out of the hot cluster atmosphere. That part of the story had solid observational support for years. What was consistently missing across essentially every previous study of this kind was clear, direct, dynamically confirmed evidence of the other half of the cycle. Cooling gas actually condensing out of that hot atmosphere and flowing back inward, all the way down to the black hole's immediate feeding zone, caught in the act, with measured velocities proving the direction of flow. Researchers had seen filaments before, including in NGC 4696 itself in Hubble's earlier images. They'd inferred, based on X-ray observations, that gas cooling must be happening somewhere within these systems, because pure heating without any cooling and resupply simply doesn't match what we observe about long-term black hole growth. But inferring that cooling and inflow must be happening somewhere, in some form, is a very different thing from actually measuring it directly. Watching gas move in real time along a specific traceable pathway from the outer filament all the way into the feeding disk. That's the specific gap that the new NGC 4696 observations close. It's the first time researchers have assembled dynamically confirmed evidence for the complete loop, not just the heating half, and not just an inferred cooling half, but an observed, measured, velocity-mapped connection between infalling filaments and a black hole's feeding disk, all captured within a single, unified dataset. This is why so much of the coverage and commentary surrounding this discovery has used language like solving a decades-old puzzle, or the final piece, or the missing link. It's not hyperbole. Within the specific narrow technical question of how cooling gas actually gets from a galaxy's hot atmosphere into a black hole's feeding disk, this observation genuinely does represent the clearest, most complete answer astronomers have ever obtained. Of course, one clear answer in one galaxy raises an obvious next question. Is NGC 4696 special? Or is this the norm? Is what we're seeing here a universal process, playing out in galaxy after galaxy across the cosmos? Or did we just get lucky, catching one particular system at one particular moment, in one particularly favorable orientation? That question is exactly what researchers are turning to next. Every good scientific discovery closes one question and opens several new ones, and this result is no exception. Researchers are already looking ahead to the next stage of this investigation, and there are a few clear directions this work is likely to take in the coming years. The most obvious next step is simply expanding the sample. NGC 4696 was chosen carefully. It's relatively nearby. It's the dominant galaxy in a well-studied cluster, and it had already shown tantalizing hints of structure in earlier Hubble images, making it a strong candidate for this kind of deep, time-intensive follow-up study. But a sample size of one galaxy, however compelling, can't tell you whether a phenomenon is universal or unusual. To answer that, astronomers need to point NIRSpec, or instruments like it, at other central cluster galaxies, and see whether they find the same kind of filament-fed, rotating disk structure, or something different. There's good reason for cautious optimism here. Many other central cluster galaxies show broadly similar features to NGC 4696 in earlier X-ray and optical observations, hints of filaments, evidence of past jet activity, similar hot atmospheres surrounding them. If Webb-class observations of several of these systems reveal the same basic pattern, infalling filaments connecting directly to spinning, circumnuclear disks, it would strongly suggest that this feeding mechanism isn't a quirk unique to NGC 4696, but a genuinely common, perhaps even universal, process by which many, if not most, large elliptical galaxies keep their central black holes fed. On the other hand, if other systems turn out to look quite different, disks without clear filamentary connections, or filaments that seem to be flowing outward rather than in, or systems that show no organized disk structure at all, that would be scientifically interesting in an entirely different way, suggesting that black hole feeding might follow multiple distinct pathways depending on the specific conditions in a given galaxy, rather than one single universal mechanism. Researchers are also interested in comparing weaker feedback systems to stronger ones. NGC 4696 sits at the center of a cluster with clear evidence of past, moderately strong jet activity. Comparing this system to central galaxies with historically weaker jets, or historically much more powerful ones, could help reveal how the intensity of a GN feedback affects the pace and structure of the resulting cooling and reaccretion cycle, essentially mapping out how the thermostat behaves under different conditions. There's also enormous scientific value in pushing this kind of observation to more distant galaxies, further back in cosmic time. This is technically much harder. More distant targets are fainter, harder to resolve at fine spatial scales, and require substantially more observing time to achieve the same signal quality achieved for the relatively nearby NGC 4696. But if researchers can eventually apply similar techniques to galaxies as they appeared several billion years ago, when the universe's overall rate of star formation and black hole growth was near its historical peak, it could offer a much more direct test of whether this filament-fed recycling mechanism was actively helping drive black hole growth during that critical era, rather than only in the relatively quiet present-day universe. And there's a final, broader ambition worth mentioning: refining the connection between these detailed, small-scale observations of individual feeding events and the large-scale computer simulations that cosmologists use to model the evolution of galaxies across the entire history of the universe. Those large cosmological simulations, with names like Illustrating E, AGLE, and others, rely on relatively simplified, approximate prescriptions for how a GN feedback works, because simulating the full detailed physics of jets, gas cooling, and filament formation across an entire simulated universe containing millions of galaxies is computationally far beyond what's currently possible. Detailed, real, observationally verified case studies like NGC 4696 give theorists crucial, concrete benchmarks that can be used to test and refine the simplified feedback models embedded within these enormous cosmological simulations, hopefully making them more accurate and more physically realistic as a result. In short, NGC 4696 has answered one specific long-standing question with real confidence. But it's also handed the field of astrophysics a template, a working example, and a whole new set of tools and techniques that researchers are already planning to apply, system after system, in the search for a more complete, more universal understanding of how the largest black holes in the universe manage to keep growing across cosmic time. It's worth pausing here and asking an honest question. Why should any of this matter to you? You are never going to visit NGC 4696. No spacecraft humanity will build in your lifetime, or probably in the lifetime of anyone who's ever been born, will travel the 145 million light years required to see this system up close. So why spend an hour and a half of your life thinking carefully about how gas filaments feed a black hole in a galaxy you'll never see? Here's one answer. Supermassive black holes are not some exotic, irrelevant footnote in the story of the universe. They are, in a very real sense, architects. The energy released by feeding black holes and the jets they launch appear to play a decisive role in regulating how many stars a galaxy is able to form over its entire lifetime. Without that regulating influence, galaxies like the Milky Way might have formed far more stars than they actually did, burning through their gas reservoirs far too quickly, producing a galaxy that would look and possibly host planetary systems very differently than the one we actually live in. Our own galaxy has a supermassive black hole at its center, Sagittarius S star, currently fairly quiet, not actively feeding in any dramatic way, but not necessarily permanently so. Over the Milky Way's roughly 13 billion year history, there's reason to believe our own central black hole has gone through episodes of much more active feeding, complete with its own jets and its own feedback cycles, shaping the galaxy we call home in ways we're still working to fully understand. So when we study the physics of how a black hole in a distant cluster gets fed, we're not studying some isolated curiosity, disconnected from anything relevant to us. We're studying one of the fundamental processes that shape the galaxy in which every star, every planet, and as far as we currently know, every living thing in the universe happens to reside. There's also something worth appreciating here about the nature of scientific progress itself, independent of any specific practical application. For most of human history, the question of how black holes are fed was simply unanswerable, not because nobody was clever enough to ask it, but because the tools required to answer it didn't exist yet. It took the combined effort of ground-based X-ray observatories, decades of theoretical modeling, an earlier generation of space telescopes like Hubble, and finally, an instrument as extraordinarily sensitive as Webb's NIRSpec, operating from a vantage point a million miles from Earth, to finally gather enough precise, detailed information to settle the question. That's worth sitting with. We built a mirror 6.5 meters across, coated it in gold, folded it up like origami, launched it on a rocket, unfolded it in the vacuum of space with essentially zero margin for error, cooled its instruments down to a fraction of a degree above absolute zero, and pointed the whole apparatus at a galaxy so far away that its light left before there were flowering plants on Earth. And from all of that effort, we extracted a definitive answer to a question that had puzzled some of the sharpest minds in physics for half a century. There's a reason astronomy tends to produce a particular kind of humility in the people who study it closely. Every discovery like this one is a reminder of how much remains unknown, even as it closes off one small specific corner of ignorance. Solving the mystery of how NGC 4696's black hole gets fed doesn't mean we now understand everything about black holes or galaxies or the universe. It means one very specific, very carefully framed question. How does cooling gas actually travel from a galaxy's hot atmosphere into its black hole's feeding disk? Finally has a solid, direct, observationally confirmed answer, at least in this one system. And already, that single answer is reshaping how researchers think about a much bigger set of questions. How black holes grew fast enough in the early universe to produce the billion solar mass giants. Webb keeps finding it incredibly early cosmic times. How galaxies regulate their own star formation over billions of years. And how the relationship between a galaxy and its central black hole, a relationship astronomers have observed statistically for decades, without ever directly watching it play out, actually operates, moment to moment, gas particle by gas particle, across cosmic history. That's the real value of a discovery like this one. Not that it answers everything, but that it answers something specific, something concrete, something that had eluded astronomers for decades. And in doing so, it hands the entire field a sharper set of tools for tackling everything that still remains unknown. Before we wrap up, let's run through a handful of questions that tend to come up whenever a story like this makes the rounds. Some of the things you might be asking right now. Is the black hole in NGC 4696 dangerous to us? Not even slightly, and not just because of the distance. Though 145 million light-years is, on its own, an overwhelming amount of separation. Even if this black hole were somehow relocated to the center of our own galaxy, replacing Sagittarius S star, its gravitational influence would only be significant within a relatively small region immediately surrounding it, a region measured in light years, not the kind of scale that would ever threaten Earth or our solar system, which sits tens of thousands of light years from the galactic center. Could our own Milky Way's black hole be doing something similar right now? Possibly, though not as dramatically. Sagittarius S star is currently in a relatively quiet, low-activity state compared to the actively feeding black hole in NGC 4696. It's not currently launching powerful jets or visibly consuming large amounts of material. However, there is evidence, including some structures observed near the galactic center, suggesting our own black hole has gone through more active feeding episodes in the past, and theoretically could again in the future, potentially involving similar processes of gas cooling and filament formation. Just on a smaller scale, even the differences between the Milky Way and a massive cluster-dominant elliptical galaxy like NGC 4696. Does this discovery mean black holes will keep growing forever? Not necessarily forever, but the self-regulating nature of this cycle does help explain how black holes can continue growing over enormously long timescales, without either starving themselves out or growing without any limit. Over the extremely long term, trillions of years into the future, well beyond the era when new stars can still form, the picture changes dramatically as galaxies eventually run out of fresh gas altogether. But within the timescales relevant to the current era of cosmic history, this recycling process appears to be a key part of how black holes sustain their growth. How confident are astronomers in this result? Quite confident for a few converging reasons. First, the result is based on direct, measured velocity data from NIRSpec, not just an inferred interpretation of a still image. Second, independent magnetohydrodynamic simulations, built from fundamental physics rather than tuned to match the observations, reproduced a strikingly similar filament and disk structure. Third, the result has been peer-reviewed and published in a major, well-respected astrophysics journal, meaning independent experts in the field have scrutinized the methodology and conclusions before publication. That said, as with any single result in science, researchers will want to see this pattern confirmed in additional galaxies before treating it as a fully universal, settled feature of how all black holes are fed. Why did it take until 2026 to find this, when Hubble photographed the same structure years earlier? Because Hubble's instruments, while excellent at capturing sharp, high-resolution images, weren't capable of measuring the fine-grained velocity information needed to determine whether the gas in that structure was actually falling inward or just sitting there. That required an integral field spectrograph sensitive enough to resolve motion at a scale of tens of light years, in a target 145 million light years away, a capability that simply didn't exist in any prior space telescope, and only became available with Webb's NIRSpec instrument. Is NGC 4696 unique, or are there other galaxies like it? Researchers strongly suspect it isn't unique, given how many other central cluster galaxies show broadly similar characteristics: hot surrounding atmospheres, evidence of past jet activity, and hints of filamentary structure in earlier observations. But confirming that requires repeating this kind of detailed, time-intensive NIRSpec observation on additional targets, which is exactly the next phase of research the team and others in the field are now pursuing. Let's bring everything together one more time from the top. Supermassive black holes sit at the centers of nearly every large galaxy in the universe, and they grow by feeding on infalling gas. But that feeding process is, by nature, violent. It produces powerful jets that blast outward and heat the surrounding gas, which should, in theory, choke off the black hole's own fuel supply. For decades, astronomers understood this as a paradox and suspected that some kind of self-regulating cycle must exist. Gas heated and expelled by the black hole eventually cooling, condensing and falling back inward to feed it again, but lacked direct observational proof that this cycle actually happens. NGC 4696, the giant elliptical galaxy at the heart of the Centaurus Cluster, 145 million light-years from Earth, had already shown hints of this process in earlier Hubble images, a strange hook-shaped swirl of gas near its central black hole. But Hubble could only show shape, not motion. The James Webb Space Telescope, using its NIRSpec instrument across nearly 8 hours of observation, finally measured that motion directly. It confirmed that the swirling structure is a rotating disk of gas, 800 light-years across, spinning at speeds up to 600 kilometers per second, and that this disk is directly connected to a large infalling filament of gas, actively funneling material inward from the galaxy's wider surroundings. Follow-up magnetohydrodynamic simulations, built independently from fundamental physics, reproduced the same filament and disk structure and revealed that magnetic fields likely play a key role in guiding cooling gas into these narrow, organized channels, rather than allowing it to fall in a smooth, spherical, unstructured pattern. Together, these observations and simulations provide, for the first time, direct evidence for the complete self-regulating feeding cycle theorists had long suspected. Jets heat the surrounding gas. That gas gradually cools and condenses into filaments guided by magnetic fields. Those filaments feed a rotating disk around the black hole, and that disk continues to funnel material inward, restarting the entire cycle. This discovery helps explain how supermassive black holes can sustain growth over billions of years without permanently starving themselves, and it offers a valuable, real-world template that may help explain, at least in part, one of astronomy's biggest current puzzles: how some black holes manage to grow to enormous sizes within the first billion years after the Big Bang, far faster than simple accretion models would predict. Researchers are now planning to extend this kind of observation to other galaxies to determine whether the filament-fed, self-regulating cycle observed in NGC 4696 is a universal feature of black hole growth, or a pattern unique to this particular system. There's a particular kind of image that tends to stay with people after they learn something like this, and for me, it's this one. A galaxy sitting quietly, 145 million light-years away, going about a process that has been running essentially unnoticed by anyone for as long as that galaxy has existed. Gas heating, gas cooling, filaments forming, falling, feeding a black hole that then heats the gas all over again. A loop with no beginning and, as far as we can tell, no scheduled end, running quietly in the dark, indifferent to whether anyone was ever watching. And then, for 8 hours in the summer of 2026, someone was. A telescope built by thousands of engineers and scientists, launched on Christmas Day, parked 1 million miles from Earth, pointed its most sensitive instrument at that exact spot in the sky, and finally watched closely enough, precisely enough, patiently enough to catch the process in the act, to trace, for the first time, gas actually falling, moving, feeding a black hole in real time, rather than inferring it from a still photograph or a theoretical model. That's what this discovery really represents. Not just an answer to a decades-old technical question about accretion physics, though it is that. It's also a reminder of what becomes possible when a civilization decides that understanding the universe is worth the enormous cost, effort, and patience required to build the tools capable of actually seeing it clearly. Somewhere out there, right now, in NGC 4696, and in countless galaxies like it across the observable universe, this cycle is still running. Gas is heating, gas is cooling, filaments are forming and falling, Black holes are feeding and being fed in a slow, patient rhythm stretched out across timescales that make a single human lifetime look almost meaningless by comparison. We can't see all of it. We probably never will. But thanks to this discovery, we understand, with far more confidence than we ever have before, exactly how the process works. And that, in the end, is what science does. Not by claiming to know everything, but by patiently, carefully, taking one more piece of the unknown and making it known. Thank you for spending this time with me. If you want to go deeper into any part of this story, the physics of accretion disks, the history of the Centaurus Cluster, or how Webb's instruments actually work, let me know in the comments, and I'll consider it for a future video. If you found this useful, consider subscribing, and I'll see you in the next one.